Hello everyone, welcome to this week's Crunch seminar. The first talk for today is about a Wachspress-based transfinite formulation for exactly enforcing Dirichlet boundary conditions on convex polygonal domains in physics-informed neural networks. This is given by Professor N. Sukumar from UC Davis and Dr. Ritwick Roy from Simulia. Professor Suku holds a PhD in theoretical and applied mechanics from Northwestern University. He held postdoctoral appointments at Northwestern and Princeton University before joining UC Davis in 2001, where he is currently a professor in civil and environmental engineering. Professor Sukumar is a regional editor of International Journal of Fracture, a member of the editorial boards of Computer Methods in Applied Mechanics and Engineering, and Finite Elements in Analysis and Design. Sukumar's current research emphasis is on novel discretization-based methods, such as virtual element methods, on polytopic meshes and applications of deep neural networks to solve partial differential equations over complex geometries. Professor Suku was also a visiting scholar at the Crunch Group, Brown University in 2023. Dr. Ritwick Roy is a director of structures software engineering R&D at Dassault Systems, Simulia. He earned his PhD in computational mechanics from University of California, Davis in 1999 and joined the Abacus R&D team at Hibbett, Carlson, and Sorensen, now called Simulia. Over his career, he has contributed to numerous core development projects, including constraint solver, airbag technology, occupant safety for crash simulation, and discrete particle methods. More recently, his work has expanded to include AI and machine learning initiatives at Simulia. In 2021, Dr. Roy completed his MBA at the Questrom School of Business, Boston University. He also teaches part-time at Questrom, covering topics such as data analytics and the ethical use of AI in business. With this brief introduction, I invite both Professor Suku and Dr. Roy to present their work.
Thanks, Vivek. I'll start off with the presentation, and then midway, Ritwick will present the numerical results. So first of all, I must acknowledge a lot of discussions when I was at Brown with George and also many members of the Crunch group, and some of them are probably also listening here. So this work is based on what I'm going to call a Wachspress-based transfinite formulation. And in the title, two things may be new to many of you. One is the Wachspress. What are Wachspress coordinates? I'll talk about that. And also, what is transfinite? So transfinite is interpolation is basically, instead of classical data interpolation where you have a bunch of points, now I would like to interpolate over edges or curves or surfaces. So just to illustrate this idea, so what is the main goal is that if I'm given a polygon like this, and I'm given functions on each edge which are prescribed such that they are continuous at the vertices, I want to construct an interpolant that extends into the domain and which is continuous. So that is the first goal. And then subsequently, I want to embed this into a neural network in some fashion so that the neural network approximation exactly satisfies the boundary conditions. So that's the main focus of this work. So I'll begin with some background and motivation on essentials of generalized barycentric coordinates, and also why we want to pursue this compared to what has been done before. Then a short introduction of what are techniques to impose boundary conditions in pins. And the first example one might think is probably very simple. It's just one-dimensional, but I think it's very instructive to understand the idea in one dimension, because essentially we are using the same principle which will guide us in multi-dimensions. So in 2 dimensions, I'll talk first about some examples of Wachspress coordinates and show you some plots and its connection to computer-aided geometric design, because you can think of geometric design and approximation theory are basically 2 sides of the same coin. In geometric design, you're trying to basically blend curves which are given in space, whereas here you want to basically blend patches or blend approximations via patches together, right? So an important instance of this is what's called a Coons interpolant, which arises in geometric design and also has been used in interpolation, for example, finite element interpolation in mesh generation. And there's a notion of then this transfinite interpolant I mentioned before, So I'll use that to construct Dirichlet boundary conditions over polygons and then show you the network approximation. And then I'll summarize, and then Ritwick can take over from there, right? So let's start off with the background and motivation. First, let's look at the strong form of a boundary value problem. And here I'm starting off with a heat conduction or the Poisson boundary value problem, where you use what you want to look at, want to find out, which is the temperature. F is a heat source or heat sink, and is 0. So this is the strong form equation, which is a second order partial differential equation. And I'm assuming Dirichlet boundary conditions. So U is prescribed to be some function G. And of course, it can have different functions on each segment, as long as we are assuming that the entire U is a continuous function on the boundary. So this is the strong form, and associated with that, we also often have what is called a weak form or a variational form. And with that, you can also construct a variational principle. So what is that? You can define a bilinear form, AUW, is just which involves their first derivatives, gradient of U dotted with gradient of W. So U is called the trial function, and W is called the test function or variation. So this is a bilinear functional, and this is a linear functional on the right, L of W, which is just the force times the test function or variation. And these are integrals over the domain omega. So the variational principle states that the solution of this strong form can be posed as a minimization of the potential energy pi, which is half times AVV, where you put both V in both slots, minus L of V, subject to the condition that V must lie in this space. So V must be in H1, so its derivative and the function must be square integrable. But more importantly, this in red, V must be equal to G on del omega. Otherwise, you cannot do the minimization, strictly speaking. So it must be what is called kinematically admissible. So the application of this in a neural network setting is what is called deep Ritz by Weynan and BU. So let's assume that n theta of x and theta is the neural network output. So what one must then do, say, I want to construct a trial function, which I'll call u theta of x and theta. And the objective is that I'll somehow have to use n theta, the output of the neural network, to form u theta, but mindful that u theta must belong to S, must belong to the space S, so that it's kinematically admissible. And a consequence of that is that pi of u theta will be always larger or greater or equal to the exact potential energy. So you'll always converge to the exact from above, and you cannot be below the exact. So that's a good way to monitor the solution. And I think Ritwick will show one example at least where we can see how we can monitor the value of pi and see how accurate the solution is, at least assess it. Okay, so now let's get to barycentric coordinates, and in particular, generalized barycentric coordinates on polygons. So most of you are likely familiar with barycentric coordinates on simplices or triangles, for instance, which are basically finite element shaped functions, or what are called barycentric coordinates on a triangle. But with n, when the number of vertices is equal to 4 or larger, these become non-unique. The barycentric coordinates become non-unique. So here I'm showing you a pentagon here, where the barycentric coordinates satisfy the property that they all lie between 0 and 1. So they are non-negative, and they can only become 0 on the boundary, and the maximum value is 1. So they additionally have this property, they are non-negative. They sum to 1 at any point, and they can reproduce affine functions. So they essentially can reproduce, say they're linearly complete. So they are suitable for use in a finite element context, and that's one more application of these barycentric coordinates. But you can also think of them as basically essentially extension of finite elements from triangles to polygons. And these are now shape functions for a polygon. So you can think of them as, they are 1 here at this vertex. The lambda of 1 is going to be 1 here, and it'll be 0 on all the edges which are not connected to 1, and it'll go linearly on this edge and linearly on this edge. So the sum of lambda 1 plus lambda 5 will be equal to 1, and they'll be, of course, because of these conditions, they'll be strictly linear polynomials on these edges. So they'll be reduced to linear polynomials, even though initially they are not polynomials. They could be rational functions or even non-rational functions, as I'll show you afterwards, right? So that's the background of this. And the interest of this is that eventually we're going to be using these lambda as basically a geometric layer in the neural network. And that's why I wanted to bring this up early on itself, to remind you that essentially we're going to use lambda as my inputs to my neural network. And this will come up also later on. So what are the different types of coordinates which are around? One of the earliest ones was Wachspress-based function, developed by Wachspress himself in 75, where he recognized that you cannot construct polynomial basis functions on a finite element mesh which consists of polygons. They must be rational functions. So that's what was done. And a lot of interest in this area came around in the early 2000s in the area of geometric design and computer graphics, stemmed by the work of Mike Floater in 2003, where he proposed mean value coordinates which could interpolate both to convex as well as non-convex polygons, though they lose the signed property, they can become negative for non-convex polygons. Of course, we know harmonic coordinates, if you solve the Laplace equation and you have boundary data, which is the maximum or minimum from the maximum principle, so they are strictly non-negative inside. That's one more application. And also my own work in maximum entry coordinate, where I used the entropy sort of functional to basically pose a maximum problem. So like a regularized. So just going back to quickly to my previous slide. So you can see that this has one equation, and in 2 dimensions, this has 2 equations. So you have 3 equations and 3 unknowns if you have a triangle. So the problem is unique. The solution is unique. But once you go to 4 equations with 3 unknowns, 4 unknowns and 3 equations, the problem is underdetermined. So there are infinite solutions. So not surprisingly, here are a few solutions which you get. So that's my work. And the applications in geometry processing are shown here. Some of them are like transfinite interpolation. You can do color interpolation now. If you can directly interpolate on convex or non-convex polygons, you don't need to split up these polygons into triangles, or you can do mesh deformation and warping by enclosing your object or your which you want to move into a cage and just deform the cage. Because it has this non-negative property, your horse will always remain inside this polyhedral cage. So these are some of the applications which people have pursued in geometry processing. Okay, now coming to why we wanted to do this work, of course, it overcomes a prior limitation, which was my own work in 2022. I'll just quickly show this one slide to illustrate what was the main issue. So let's consider a square with 0, 1 square and assume the boundary condition is 0, right? So you have essential boundary conditions which are 0 on the boundary. So here the boundary consists of 4 line segments. So you can construct an approximate distance function using what is known as the R equivalence formula in this paper. And you can think of it as just like a harmonic mean of these 4 functions. So these 4 functions are basically correspond to an approximate distance function to each segment. And if you take this sort of 1/4 of the harmonic mean, it'll ensure that the 0 level set of all these 4 functions is preserved. So just to show you this plot, this is what this function looks like. So you can see that it's clearly 0 on the boundaries, and it's basically this function which is strictly positive in the interior. But a consequence of this choice is that the Laplacian of this function phi blows up at the vertices. So that's not surprising, because what you're trying to do is you're saying that when you construct these functions phi1, phi2, phi3, phi4, you're saying that phi1, phi2, phi3, phi4. So phi1, for example, must be 0 here, and its normal derivative must be 1. And the same thing is true about here. This is 0 here, and the normal derivative is 1. But that's a conflict, because when you have a normal derivative of 1 here on this edge, these values cannot be 0. So that's what happens. So the Laplacian basically, the gradients are bounded, but the Laplacian basically blows up. A consequence is that now if you think of your trial function in a neural network as just phi times n theta, so you want to impose 0 boundary conditions, but now the Laplacian of u theta will also blow up at these vertices. So what we did in the previous paper was to choose basically a smaller square with some delta and use a small tolerance, but still a finite tolerance, so that you did not choose collocation points which were very close to the boundary. And what we are going to show you here in this talk is that we're going to use this Wachspress-based transfinite formulation to basically overcome this limitation from the previous work. So just to sort of set up some notations, because there'll be a lot of notations coming up to the latter part of the talk. So I just thought I'll put all of them in one shot. So the calligraphic L will be denoted as a lifting operator. Basically, you're lifting functions from the boundary, which are given to you, to the interior of the domain. And in one dimension, you have 2 values prescribed on the boundary, and you want to construct a lifting operator that extends this function into the interior. Then we also have a projection operator by this this character P, where this will arise when I do basically a polygon. So here I'm going to basically create a projection of these barycentric coordinates on the polygon onto the faces. And I'll come to that when I'm there. So the third is I'm going to denote B as a boundary, encapsulate all the functions on the boundary into one single function, beta, in B in terms of all the barycentric coordinates for the polygons. Then in terms of neural networks, we'll assume that n theta with a scalar x is a univariate neural network output. U theta ADF is what we did in the earlier work, is the neural network ansatz with the ADF. approximate distance function. I'll use TFI for the transfinite interpolant approximation, and that'll be with this. In the one-dimensional, you can just use X itself. Now, when you go to polygons, I'm going to use lambda here, where I mentioned to you, they basically lie in between 0 and 1. So the n functions that are there, which are coordinates. And then again, n theta, but now it'll be a function of lambda itself, that'll be like a geometric feature, you can think of it. And in a classical setting, you would use with ADF, you'll just call it U theta of ADF. And U theta of TFI will be what I'm going to construct in my last slide, essentially. And these are which may appear in also Ritwick slides afterwards, so that you have a sense of what I'm going to talk about subsequently. So let's look at imposing boundary conditions. So there are two sort of popular ways. One is the soft imposition of Dirichlet boundary conditions, where incorporating a boundary loss term, and this was sort of introduced, or at least used extensively for forward and inverse problem in the seminal work of George and the paper by Ricey et al. In JCP. And the other way is to do a hard imposition, or in some cases, you can do an exact enforcement of Dirichlet boundary conditions. So going back to the early works of neural networks, they use simple polynomials in one dimension or on Cartesian geometries. So they served as level set functions to form the neural network ansatz. Or in addition, there's also work of Berg and Nystrom early on, where they use a low capacity neural network to form an approximate distance function to the boundary. But of course, in this case, it's not exact because there'll be some error in the neural network itself. Then there's also interesting work on theory of functional connections, where you construct in 1D and also on squares, where by Mortari and others, where you can basically form a constrained expression with a free variable or a free function, which can assume Chebyshev polynomials or neural networks, or even Fourier series, right? In 1D and on 2D, where you want to construct a priori, essentially the same goal of constructing an approximation or an interpolant which interpolates data or curves. And just to point out that TFC on a square is basically identical to Coons patch, which I'm going to show you afterwards. And of course, the work I showed you just before on our own work earlier on approximate distance function. Of course, this is not exhaustive. There are many other techniques, but this essentially summarizes what is soft and what is hard. And that's what is going to be important later on. Okay, so let's look at one dimension, because it's instructive to look at one dimension before going to two dimensions. So let's think of a closed interval omega bar, which is -1 to 1, with Dirichlet data at the two ends. So U minus 1 is equal to U1 bar, and U of 1 is equal to U2 bar. So this is the Dirichlet data, and they stem from a function, say U of x, that is, this function U of x, and you're putting the boundary conditions based on that function. So if you just use linear interpolation or barycentric interpolation, then it's seemingly the obvious choice is to define a linear function or an affine function, G of x, which interpolates these two data. So you're given U1 bar and U2 bar, and now you say, okay, I'm going to use 1 minus x by 2 U1 bar plus 1 plus x by 2 U2 bar, where you can clearly see that where L is now a lifting operator. You can just think of this as a lifting operator, where it acts on a function whose boundary data you're using. So I'm using U1 bar and U2 bar from U, and then creating something that extends into all of the domain, right? Basically into omega bar. So now I can compute this anywhere inside omega bar. So that is the notion of this operator L. So whatever it acts on, it takes whatever the boundary data is from this function and then extends it into the domain. And that's the basic thing that we'll use again and again very often. And what is in this one-dimensional setting, in fact, what happens is that G of x is also the harmonic extension, or what is called the harmonic lifting, because G of x is the solution of the Laplace equation with precisely these two boundary conditions. So that is a solution. It's a linear function, and this is a solution. So you can see clearly in this case that if you, just going back, that if x is -1, you get U1 bar, and if x is 1, you get U2 bar. Was there a question by anyone?
Yeah, I have a question. My name is Kamal.
Yes.
Is it unique, or I can have any other function?
Sure, you can have any other function U1 bar, because it's not unique, but this is the simplest linear interpolant, right? That's what I meant to say.
Also, is it only polynomial, or trigonometric function I can use? Sine,
oh yeah, you
cos.
can use you can use cos or whatever you want, right? Depends. But here you want to be unbiased, right? You don't want to pick particular functions to, because something is in the solution, right?
Yeah.
So that's the point. You want to use the simplest function, which will do the job, right? That's why. Yeah, that's a good point, actually. Yeah. Okay. Okay, so now, the key thing is, okay, I know G of x in this one-dimensional case, very simple. But to form the neural network ansatz, the goal is, okay, I need to add something to it, right? If I want to construct U of theta, right, which is the neural network trial function, So I must add something to it, a contribution, but that contribution must vanish on the boundary. So that's the key thing, right? So then the inference or the consequence is that, oh, what is the simple idea is to take the neural network output and you subtract its lifting, essentially. So that's the basic idea, right? That's the key idea which you add to G, basically. You say, okay, you take here, it could be any function, right? Essentially, because you take any function here and subtract its lifting, it'll identically be 0 on the boundary. And this is true in 1D or 2D or 3D or any dimensions. This is going to be true, right? This is basically the property of the lifting will ensure that this happens. So a consequence of that is you say, okay, I'll just add now, I'll form my TFI trial function to be g of x plus this lifting, this difference of the neural network minus its lifting, because this guy is going to be 0 on the boundary, and you'll recover g of x. So if you expand this lifting property of n theta of x of theta, what is this quantity? This is basically, so n theta of, so the lifting is, you're going to take the boundary values of n theta, which is n theta of -1 theta, n theta of 1 theta, and then take this linear interpolant, which is the barycentric interpolation of this boundary data. And now you can see by construction that if x is -1, you will get back basically g of -1. If x is equal to 1, you'll get back basically g of 1. And that is the boundary data. Not surprising, right? So so this idea basically will resonate throughout the paper, throughout this talk, and also in the paper which we published, right? So that's the main idea is already here, right? And one consequence we should point out here is to really compare TFI with ADF. In the context of ADF, in one dimension, you'll have a function g of x, which is the same as before. But now you can say, or you can think of, okay, I might multiply the neural network by a function that is an approximate distance function to the boundary. So at x is equal to -1 and x is equal to +1. So you can think of that as just 1 divided by, so again, the harmonic mean divided by 2. So 1 upon 1 minus x plus 1 upon 1 plus x. And this is 1 minus x squared by 2. So notice that this function vanishes on the boundary, and this normal derivative inward in the inward direction is equal to 1 on both sides, right? So they both enforce the boundary conditions, but they are differing in form. So ADF has a multiplicative structure, and it has consequences, whereas TF incorporates it additively, which is also going to be advantageous, right? So one simple consequence of an additive property is that if you have, if the exact solution resides in your neural network space, then you can recover it, basically, because if n theta can capture u of x, then you put in u of x here, and you'll get back basically u of x as u theta TFI. That's a consequence of this, but if you have a multiplicative approximation in this form, you won't be able to do that. So the second thing is that, more importantly, it couples the behavior on the boundary and the interior due to the presence of the product term, because this guy goes to 0 as you approach the boundary, whereas this guy must be active, of course, near the boundary. So this creates a competition between the two of them. And let's see one consequence of that. So if you approach the boundary, let's assume g is equal to 0, and you take its derivative, take the derivative of this. So the derivative is going to be phi prime n theta plus phi times n theta prime, which is given here. Now, near the boundary, phi is approximately 0, so I knock off this term, and phi prime is, say, plus or minus 1 on both sides. So it's approximately, it'll tend towards plus or minus n theta. So in some sense, it does not capture sufficient information about the derivative of the neural network. And the same thing can be seen if you take the gradient, as it happens in training, right? If you take the gradient with respect to theta, you just get phi times gradient of theta, because phi is not a function of theta. So you just have gradient of theta times n theta. And again, near the boundaries, this guy is going to 0. So that'll impact basically the training. So it'll impact gradient flow in residual minimization, and also it'll enhance the stiffness. So these are things to be considered. And even Ritwick's results will show that as you get closer to the boundary, the ADF training will get much more difficult, right? That's what I'll show. So now let's get to polygonal domains, and in particular, what I want to talk about, right? So the first is Wachspress coordinates, which will be the main, what will be focused on, right? So here I'm just showing you a quadrilateral, but the idea is for any convex polygon. So this was the original sort of algorithms can go back to Wachspress himself, but only in 2001, a simple formula with areas and sine and cosine formulas was introduced by Meyer et al. But a nice way to implement is in this paper from 2014 by Mike Floater, Kai Harmon, and myself, where a MATLAB code is also provided here. So what does so if you define a point x, you just need to know the edges, the normal to the edges, n1, n2, n3, n4, and the distance from the point x to an edge, which can be found out from a simple dot product. So you don't need causes and sines, which could be unstable. So this is just the formula here, ni divided by hi, and you take the two-dimensional determinant of this, and then you normalize this function, and then you can compute also its gradient if you want, right? But recall that, as I mentioned to you before, that Wachspress coordinates are rational functions, so they are not polynomials. So they are rational functions, and some of the other barycentric coordinates are not even rational functions. They have singularities. They have square root terms which appear. Okay, so and there's also a simple formula for a quadrilateral case. A couple of years ago, we derived basically an exact solution for this problem. And the idea there,
can you go back? So WIs are the
so there'll be the determinant of this two-dimensional 2x2 matrix.
I see.
So it's just a cross product, and it's just a simple way to write it.
Yeah.
And then you normalize it. So, but at least for the quadrilateral, can I go ahead?
Yeah. So then the last formula just comes out from the identities, right?
Yes.
For the gradient of lambda is.
Yeah. That's just from this. They're taking the derivative of this.
Yeah.
Yeah.
Okay. All right. Yeah. Thanks.
Yeah, but I think for a quadrilateral case, life is a lot simpler, and that's based on this work which we did 2 years ago. Because just going back to the problem I posed you before, right? So we had three constraints. Summation of lambda 1 is 1. So summation of lambda times lambda dotted with x, right? Lambda 1 x1 plus lambda 2 x2 is equal to x. And lambda 3, again, lambda 1 y1 is equal to y. So you have three equations, but now you have four unknowns. So what is the missing equation? So that's what we found out, in this paper, where we also do mean value coordinates. So in fact, rho 1 turns out to be sort of the product of the areas, it turns out. This product is like a product of two areas. And if you solve this, you basically get an analytical solution for Wachspress coordinates for a convex quadrilateral, right? For essentially. So there's no need to do any algorithms or the previous slide, because you can get an exact solution for this problem. And then, of course, it's differentiable everywhere and no problems, right? So that's the benefit of this.
So rho I has a geometric interpretation?
Yes, it has. Yes, it has. It's a product of areas, essentially, of the two areas which will appear. I can go back if you want. Yeah. So Li times Hi minus 1, you can think of it as basically, this area. Suppose you have two adjacent edges, this edge and this edge, right? So it's product of this area and this area.
So you form I see. So you form two triangles from the barycentric point.
Right.
And then you take so rho I is the I guess normalized area of
it's a normalized, because the
normalized area of those
appear.
Two triangles. Okay.
Yeah. But there's a lot more theory to it, of course, because we want to make this a full rank, and there's a lot of linear algebra.
But rho has one index, so that's why. Can you go back rho 1, for example? Can you show us rho 1 on that?
Sure. So suppose you take the index 1, right? This is here, right? So rho 1 is connected to this edge and this edge.
Oh, okay. So you follow the vertices.
So two triangles.
I get it. You follow the vertices.
Yes, exactly. Right. So because it gets, so this will also appear in what I'm showing you afterwards, right? Any vertex will have two contributions, right? From both edges, right? It's connected to, right? So the point of this is that, well, you can just have a simple formula, and then you can just implement it, right? Of course, once you know the solution, you can compute its gradient derivative exactly.
And so if you go to 5, pentagon,
right? So it's a lot more tricky, because we've been struggling with it for the past year or two, right? Trying to come up with a formula.
Also, there's no simple formula.
Yeah, there's no. It's not. In fact, this was the first. Sure. This was. In fact, DHE and Defonso, I think in his PhD, he's at Georgia Tech, and he's a professor in math at Georgia Tech. So they developed. They were doing dynamical systems where they came across mean value coordinates in a different context, right? For constructing interpolants on Filipov surfaces and all that, right? So there they came across this, and I met Fabio a few years ago in in Italy, and then talked to him about this idea of using it for it's going to be useful for other applications of GBCs, right? So that's how it came around, right? Yeah, but there's a whole theory of how do you make this underdetermined system full rank. Essentially, you want to make it, right? So you want to add equations so that you get a unique solution, essentially. So that's what you want. That's the objective of this exercise, right? So
Great,
based
thanks.
on sign patterns and all that stuff it has, right? Yeah, but it's a very interesting topic. At least I think so. Okay, so for a polygon, so these are some shape functions shown. So these are like finite element shape functions. If you just show it to someone, they won't think it's any different, really. But these are actually Wachspress coordinates. So on a square, Wachspress and bilinear finite elements are the same, but they become different as you go to different shapes, basically, right? As you can see here. So they have one on.
Am I not audible?
Question?
Oh, yeah, sorry. I just had a question. I just wanted to confirm that the polygons where Wachspress coordinates are harder to define, there you use mean value coordinates. Is that correct?
No, but mean value coordinates can become negative if you have a non-convex polygon.
Right.
And also on a square, I forgot one thing. Yeah, that's a good point. On a square, mean value coordinates will not give you back bilinear finite elements. Right. And also, if you want, now that you're asking, I can tell you that mean value coordinate is shown in our paper that the mean value coordinates does not have bounded Laplacian. So it kind of defeats the purpose, right? On a square itself, right? Whereas Wachspress coordinates are C infinity. They are infinitely smooth because all of them, their singularity is only outside the polygon. So they have something in the denominator that can vanish only outside the polygon. So they are infinitely smooth. So you can keep taking these derivatives, right? The functions themselves.
But I think they're not well defined on like star-shaped structures or something like that, right?
Sure, but their star shape will not be convex.
Oh, yeah. Okay. Yeah.
Yeah. So for convex polygons,
Yeah.
right? Yeah. So for convex polygons, they are well defined and they're the simplest to use.
Okay.
Yeah.
Thank you.
Yeah. Okay. Okay. So now I'm coming to the main topic after a while, right? But okay. So now just a quick. So I think I mentioned to you the importance of this in computer-aided geometric design because there you're trying to basically blend curves or blend curves that are given to you. So you prescribe, say, 4 different curves in 3 dimensions, and you want to fill the hole or find a surface that matches it exactly, either in a bilinear fashion or a bicubic fashion, if you want also derivative smoothness, right? So that's the whole idea of what are called bilinear or bicubic Coons patch, which came around in 1967. So they basically map a square to a curved quadrilateral with given boundary curves. And I mentioned right in the beginning that this notion of blending curves is sort of similar or identical, essentially, to blending approximations or blending interpolants, which are given on the boundary. And that's the perspective we'll take here. And the generalization to triangles was shown here. And there's a lot more sort of work in the barycentric, in the polygonal sphere also, because they were trying to basically construct, instead of quadrilaterals, how about doing it on polygons and trying to basically blend surfaces based on that using side blending and corner blending functions. And there's a review article in 20 where they show the whole trace of the history of this topic. So what is the work we are going to adopt is this very interesting work by Randrea Narivoni, where he used projection operators to construct generalization of Coons patches to convex domains. And the idea is to tailor this for pins. So that's the main topic, and that's what I'll convey. But first, I thought I'll just show you what are Coons patches from a slightly different perspective. Right, so let's take this unit square again. And let alpha 1x be the function here, alpha 2x is prescribed here, alpha 3x is the function here, and alpha 4 of y is these 4. So these 4 functions is given to you, right, which I'm prescribing, and they're continuous. So the value here matches. So basically alpha 1 of 0 matches alpha 4 of 0 because they both have to be the same value here, and the same thing happens at the 4 corners, right? So these are my 4 Dirichlet boundary conditions, the Dirichlet boundary functions, and their vertex values are basically those values. So you can pick alpha 1 of 0, alpha 1 of 1, alpha 3 of 0, and alpha 3 of 1 to be the boundary value, the vertex values. So what one does in Coons patch is, I'm just looking at the C0 bilinear Coons patch, is to take basically a Boolean sum of 2 linear projection operators. So if Px and Py are linear projection operators, you construct your function as this Boolean sum where you add both of them and you subtract Px, Py. And what does that mean? Essentially, it's like, think of it as a union operation. A union B is A union A plus B minus A intersection B. So we'll take a convex combination. So Px and Py represent functions that are convex combinations of opposite faces. So you take 1 minus x times this, plus x times this, right, is that, and py will be 1 minus y times this plus py of this function, right? So basically alpha 1 and alpha 3. So that is what we're going to do in the next step. And then because you're double counting the vertices, right? When you do this linear combination with this, and you do this linear combination with this, you're double counting these 4 vertices. So you subtract those contributions from the bilinear interpolation or the finite element interpolation of the 4 vertex values, or the Wachspress interpolation of these 4 vertex values. So that's what is this slide. So this is px plus py minus px py. So px is essentially 1 minus x alpha 4y plus x times alpha 2y, and py of xy is 1 minus y times alpha 1x here plus y times alpha 3x. So what is interesting to show is that, okay, I can actually think of what is this. This 1 which sticks inside can be thought of as 1 minus y plus y, 1 minus y plus y, 1 minus x plus x, and 1 minus x plus x. If I write it like this, then you can see that these bilinear functions or finite element shape functions, or I'll just call it Wachspress-based shape functions on a quadrilateral, right? On a square, sorry. These 4 functions can also be seen here, right? These can also be seen here, essentially, right? These can also be seen here. So that is what is interesting in this approximation, that now if you just focus on 1 minus x into 1 minus y, which is the vertex basis function or coordinate associated with this point. So 1 minus x into 1 minus y is multiplied by alpha 4 of y here, and it's multiplied by alpha 1 of x here, and you subtract basically its vertex value. So you can see that this shape function or coordinate is multiplied by this guy plus is multiplied by this plus this minus its value at this origin. And this idea was what was sort of motivated Dominoid to basically come up with this new idea, I thought, right? So now let's see what happens when you extend this idea, right? So if you do Wachspress coordinates on the unit square, I mentioned to you, the coordinates are the same as bilinear functions, right? So this is the picture which I would like to show you now, but in terms of the lambdas, and this is the quadrilateral. So what I would now do is to say, okay, you have lambda 1, lambda 2, lambda 3, lambda 4, which are the basis coordinate functions. And now I'm going to think of alpha 1 as just a function of lambda 2, because we know lambda 2 goes from 0 to 1 here, and lambda 1 plus lambda 2 is 1 here. And the same story happens on all the other edges. So I can think of it like this. Essentially, I'm going from 0 to 1 in lambda 2, 0 to 1 in lambda 3, 0 to 1 in lambda 4, and 0 to 1 in lambda 1. So that is the picture here. So now we will think of these parametric functions alpha I be prescribed on the boundary. On any edge, notice only 2 of them are non-zero, right? Only lambda 1 and lambda 2 are non-zero here. On this edge, lambda 3 and lambda 4 are 0, and they sum to 1. So that is the whole idea of using these lambdas as a geometric. They represent the boundary edges, and so have a geometric information embedded in them. That's the interesting point that we want to leverage. Right? So now let's come to this idea of how do you derive this. So this goes the work, this paper of Randria Narivoni essentially will be explained in the next couple of slides, but with a more sort of a physical flavor of what it does, right? So let's P be a closed bounded polygon with n vertices. Notice it's convex also, I should mention here, right? In this case. So define a boundary function B such that, so this actually, you can think of this as having 4 arguments, lambda 1, lambda 2, which becomes alpha 1 of lambda 2, which I'm going to call. This is going to be alpha 2 of lambda 3, this is alpha 3 of lambda 4, and this is alpha 4 of lambda 1. So it's a function of really one variable, because I know that the sum, even though lambda 1 and lambda 2 are both non-zero on that edge, they sum to 1. So there's really one independent variable, right? If I know one, I know the other, right? So that's the point, because they sum to 1. Right? So now let's consider an arbitrary phase pi, and let I be the set that contains the indices of the vertices that are incident upon pi. So this may be a mouthful to understand, but what it is saying is that, okay, suppose I focus on a particular index I. So I is 1, 2, 3, 4, a vertex. So what can be an arbitrary phase that is incident on it is, so pi could be either an edge, right? One edge. So there are 2 edges possible, or it could be the vertex itself, I itself. Right? Those are the possible choices for pi. And now I be the index set that contains these vertices, right? So now if you take an edge, it will have 2 vertices, right? 2 vertices for the first pi, 2 vertices for the second pi, and of course 1 vertex for the third pi, which is itself. So those are what are the vertices pi, and this is essentially so we'll define, let VQ be any vertex such that Q belongs to that index set I, and we'll define now a projection, right? So this projection is basically, in a nutshell, what this does is it takes the barycentric coordinates of a point in P bar, which is over the entire polygon, and this basically projects it onto a face, where the face can be an edge or it could be a vertex. So that's how you can think of it most easily. And that's what I'll show you in the next slide. So this is the formula. The magic formula is this one, right? So what it says is that you can think of this G of lambda as now a lifting of the boundary data into the interior, where what you do is you sum over I is equal to 1 to n, which are all the barycentric or Wachspress coordinates, and then you multiply it by this term here. And what does this term do? What you would first do is you figure out all these, what are the topological entities that are incident on I. So I mentioned to you, they are either vertex edges or vertices, right? So there are 3 of them for each I, right? And the dimension of them are going to be easy to see. The dimension of an edge is going to be 1. The dimension of a vertex will be 0. So you can see the first 2 terms will be 1 plus 1 will be 2. So this will become 1. So you get positive contributions from the first 2 terms and a negative contribution because the dimension of a vertex is going to be 0. The last term is basically you're projecting the lambdas onto the image of it, which I'm going to call mu of lambda. And that will be, again, n values, but some of them could be 0 because you're projecting onto a face. So this is the explicit formula to be used, but it's probably more easy just showing you an example. Okay, so now I'm doing the same figure before, but now what I've done is I've also marked the edges. So I put down E1, E2, E3, and E4. So let's choose I is equal to 1, just for example. So the first vertex. So the first vertex has lambda 1 in it. So lambda 1 will multiply by what is remaining in that summation which I showed you before. So let's see how to evaluate the term for lambda 1 for I is equal to 1. So in this case, you can see that the pi 1, 1, pi 1, 2, pi 1, 3 are basically two of them will be edges, E1 and E4, as I showed you before. And the vertex itself, V1. So 1, 2, 3, 4 are the vertices, right? So E1 and E4 are edges, V1 is a vertex, right? And I mentioned to you before, the dimension of this is 1, the dimension of E4 is 1, the dimension of V1 is 0. So that will go into the formula here. And what are the index sets I? The index sets I for this is going to be 1 and 2 because those are the nodes connected to this edge. The index set for edge 4 will be 1 and 4. And that is what here. The index set for 3, which is V1, the pi, which is V1, will be just 1 itself. So those are the 3 index sets I obtain. And now I want to basically compute this projection onto either the edge or the vertex. So now you can see what is the idea. So for the first case of pi, what will you get is basically the projection of the edges. If you take E1, so on E1, I know that only lambda 1 and lambda 2 are non-zero, but lambda 3 and lambda 4 are going to be 0. So its projection is going to be basically this expression. So this vector 1 minus lambda 2, 0, 0 will be the value of the image, essentially, of lambda. Likewise, for the second edge, it will be 1 minus lambda 4, 0, 0, lambda 4, because here lambda 1 and lambda 4 are non-zero, right? And they add up to 1, which is the formula which tells you, right? And of course, in the third case, this is just a vertex itself, so it will project into only 1 because we know lambda is equal to lambda 1 is 1 at itself and all the others are 0. So that is the projection here. And now I can just quickly go back to the formula to show you, okay, once I've done that, this takes a composition. You basically compose B with this argument. And now the argument is not all the lambdas, but a reduced set, which is the image, which are these guys. So now you can see what happens. So the B composed with this will be B of 1 minus lambda 2, 0, 0, B of 1 minus lambda 4, 0, 0, lambda 4, and B of 1, 0, 0, 0. So that is the contribution. And now you can compose the full term, right? All the 3 terms will be precisely B of this, B of this, B of this. And if you go back to the formula I showed you before, where this turns out to be just alpha 1 of lambda 2, alpha 4 of 1 minus lambda 4 and alpha 1 of 0. So now you can see that this has a very, very similar expression in flavor that compared to what I showed you for the Coons interpolation. If you can think of the Coons interpolation via the lens of Wachspress coordinates or just bilinear finite element shape functions, right? So that's the basic idea. But what it turns out that even on a square, this expression will not reduce to Coons interpolation, which is the same as TFC. That is to be borne in mind, because this takes in the whole functions and not just what you can do on a square, because it generalizes the whole idea to any convex polygon. So these are just some pictures showing you some plots of different. So here I take a triangle, here I take a quadrilateral, here I take a pentagon, here I take an octagon. And I impose different functions here. So there'll be linear functions, there'll be polynomial, the quadratic functions. And I took an exponential function, and I took even sines, I think so, in these examples to just compose. So this is the lifting. So this is the notion of lifting, right? So you have lifted the boundary data into the interior of the domain. So that's the basic idea here. And this is a neural network, and I mentioned to you, I think Ritwick will talk about this more. So this is the geometric or feature layer. This is the input to the neural network, and the rest is similar. This is the output, and this is how you construct the trial function. So now you have to form basically L of n theta. So this is what I told you before in one dimension. Now you just basically use lambda 1 times whatever the boundary, exactly the formula which I showed you before, but now plug in n theta instead of b into the expression. And once you do that, then the neural network trial function is just u theta of TFI is just g plus n theta minus L of theta. And if you want to do it for any convex polygon, you just change g and the definition of L, because this would change with more vertices, of course. But otherwise, the idea, of course, remains the same. So I've already gone off a bit more. So let me just summarize this and just show you this, and you can take a look at this, and in the meantime, I can answer any questions because Ritwick also has to talk. That's why.
So you're gonna show results for
Yeah. I thought
pentagons?
if someone has
pentagons?
questions, yeah, Ritwick is going to talk about the results. But if anyone has questions, I don't know.
Yeah, George, we will look at some pentagon solutions on pentagonal domains.
Okay, great.
Yeah. So let me share my screen.
Sorry, I went over to. Yeah.
Oh no. And let me go into presentation mode and guys. Yes. Okay. Can you see my screen?
Yes.
Okay. All right. So yeah, it's thank you for the invitation. It's a pleasure to be here. So let me dive into this part of the presentation here. I'm going to share with you some results of the numerical experimentation that we did with the TFI formulation. And here's a quick outline of the presentation. I'm just going to talk a little bit about the model training and then show a comparison of the ADF and the TFI method for a simple harmonic problem. And then continue on with the harmonic problem with a slightly more complex oscillatory boundary condition. And then I will show you a comparison of a collocation approach and a deep Ritz on a quadrilateral domain, followed with a nonlinear Poisson problem, and then show you a solution where we are trying to predict the solution for not just one geometry, but a family of geometries. And towards the end, I'll show you an inverse problem and end with a solution for the econal problem. So here, for the training, we actually followed a very simple approach where we have a fully connected network, as I'm showing you over here in this diagram that Suku also showed previously. A fully connected network, we went from 2 to 4 hidden layers with 20 to 40 neurons. And given the coordinates of any collocation point, we compute the Wachspress coordinates, which is fed to the input of the neural network. and the output of the neural network n theta is then used to construct the trial function UTFI. And here I'm repeating this form of this UTFI that Suku just showed you. And again, reminding you that there are three contributions: G of lambda, which captures the boundary contributions, and then n of theta, the output of the neural network, and this lifting operator. So n theta minus lifting. The G also is of the same form, the lifting operator. So the reason I repeated it over here is that you should notice that G is actually a function of lambda. So when you think about the implementation, so what we do is, given all the collocation points, we can compute the Wachspress coordinates first, and then compute the G of lambda for all the collocation points upfront one time. And then during the training phase, we just use the G over and over again. So this is kind of the standard architecture that we have used for all the problems that we've solved with this method, and we've used the tanh activation function. For the training part, we do it in two phases. First, we use the Adam optimizer, which, as you know, is very good in terms of getting around saddle points and getting close to the minimum. And when we approach the minimum, we switch over to the LBFGS to accelerate the convergence. The one thing that we did in the LBFGS phase is to use the log of the loss. The loss over here is the mean squared error coming from the PDE. And the log of the loss, again, is from the work of Urban and co-authors, where they've shown that it's a very simple modification to the training that you can do, and it gives a very good performance, training performance. So again, this is a very standard approach, simple approach that we've used for all the problems. So let me dive into the first problem, which is this Laplacian of u is 0 on this unit square, and the boundary conditions are on gamma 1, gamma 2, gamma 3, 0, and on the top boundary we have sine pi x, and the exact solution is shown over here. And the main idea over here is to compare the ADF and the TFI methods. And so to do that, what we have done is we've laid out a 10 by 10 uniform grid spanning from delta to 1 minus delta. And by adjusting delta, we can move the collocation points closer to the boundary. So here on the top row, I'm showing you the exact solution U and the norm of the gradient of the exact solution. And this is what we will be using to compare the two different methods. So what we did was we selected two different values of delta 10 to the power minus 2 and 10 to the power minus 4. So delta 10 to the power minus 4 means the collocation points are closer to the boundary. And for each of these deltas, we repeated the experiment 5 times with ADF and 5 times with TFI. And the plots that I'm showing you in the lower row are basically the training losses for these experiments. And we did it 5 times basically just to ensure that we get consistent result from run to run. So the blue curves over here are the TFI, and the red ones are the ADF. And right away you can see for that TFI outperforms ADF. We get a much lower training loss for TFI for both choices of delta. The other thing to notice is when we go from left to right, that is when we get closer, the collocation points get closer to the boundary, the TFI loss remains unchanged. Whereas if you look at the red curve, it jumps, the loss becomes worse when we get closer to the ADF. And this is again, like what Suku explained, it's due to the fact that as we get closer to the corner, the Laplacian tends to blow up and it pollutes the solution. So now let's take a look at what happens, the comparison of the solution for delta 10 to the power minus 2. So on the top left, I'm showing you the ADF and the TFI solution. And below that, I'm showing you the absolute error of the ADF with the TFI solution. And right away, you can see that for delta 10 to the power 2, the TFI solution is more accurate than the ADF. And the top right two plots, I'm showing you the norm of the gradient of the solution, and below that, the norm of the gradient of the error of the solution. And even for this, you can see that the TFI is more accurate compared to the ADF. Now let's see what happens when the collocation points move closer to the boundary of the domain. So this is the case when delta is 10 to the power minus 4. Again, on the top left, you have the ADF and the TFI solution. Below that, you have the absolute errors. And notice now that the ADF, where I'm hovering my mouse, you see the ADF solution, the accuracy has dropped significantly by 2 orders of magnitude. For delta 10 to the power minus 2, it was the accuracy of the ADF was e to the power minus 3. Now it has dropped. Whereas if you observe, the TFI has retained its accuracy level. It's of the order of 10 to the power minus 6. What about the gradient? So on the top right, I'm showing you the ADF and the TFI. And you can see for the ADF solution how the gradients are getting polluted. So, and the plots below that, where I'm showing you the norm of the gradient of the error, you can see the accuracy of the ADF solution is a lot lower as we get, for this case, as we get closer to the boundary. Whereas TFI approach maintains its the level of accuracy. So basically, this set of experiments establish that the TFI gives a better accuracy than the ADF, and also it doesn't matter where you place the collocation points, whether they are on the boundary, close to the boundary, whereas when you select the ADF approach, you need to be mindful of how you locate your collocation points. So let me move on. Now again, with the same problem, Laplacian of u equal to 0 on a unit square, but this time we are going to impose this oscillatory kind of boundary condition, sine 10 pi x, going all the way around on all the edges. Now this problem, I'll show you in the next few slides, has a specific nature. The solution is rapidly varying in a narrow band around the boundary, and then it very quickly dies out as you move to the interior of the domain. So it poses a special challenge in terms of in solving this. And for the exact solution, we use this lightning Laplace solver. And all for this problem, we use about 18,000 collocation points, as I'm showing over here, and mostly located around the domain boundary, as you can see, and a few of them sprinkled in the interior. And you will see when I show you the solution why this would make more sense. And for testing, we have even more denser grid of points located along the boundary. And here we use a decayed learning rate. And so there are this 18,000 collocation points we do in 6 batches. We do the training. And here I'm showing you on the left bottom plot the training, how the training progresses. Now, in this case, we switch over from Adam to LBFGS close to the end of the training at about at 75,000 epochs. And you'll see that really in this case, it didn't make much of a change when we switch from Adam to LBFGS for this particular problem. And here is how the solution looks like. So you have this the exact solution U on the left and in the top row, and next to it is the UTFI, and in the bottom I'm showing you this plots which actually bring out how the variation of the solution looks like. Observe how oscillatory it is along the boundary and how rapidly it dies down in the interior as you move to the interior. So this actually is, if you think about it, if you use the standard approach with soft imposition of boundary condition, this would be a very difficult, challenging problem to solve. And on the top right, I'm showing you the absolute error, and you can see that along the boundary of the domain boundary, the errors are actually relatively small, actually, and it gives you a pretty accurate, decent solution using the TFI method. And these are the x and y derivatives of, again, the same. You can see the highly oscillatory nature of the solution for this problem. So we move on again with a simple problem now on a quadrilateral domain. It's a Poisson problem that we are solving, and here the idea of this method is to try and compare the collocation approach with the Dirichlet method. And the boundary conditions are as shown over here on the right. Here what we do is, for the training purpose, we have a simple 10 by 10 grid of collocation points, which are sort of isoparametrically mapped to this quadrilateral. And for the testing, we use this denser grid of points. On the right top, I'm showing you the training loss, and you can see the switching point between the Adam and LBFGS is at 1000. And you can see we are able to drive down the loss fairly low, 10 to the power minus 12. And the middle row shows you the solution U and the exact solution in the TFI solution and the absolute error. So we get a pretty good accuracy with TFI for this problem. In the bottom row, I'm showing you the norm of the gradient of the solution. And even for that, we are getting a pretty good solution. Now, this is a relatively, I should say, this is a simple problem to solve. But TFI is able to capture the solution with great accuracy. So then now let's see the Dirichlet approach for the same problem. And as Suku explained to you, by construction, UTFI satisfies the boundary condition, and hence they form kinematically admissible trial functions for the Dirichlet method. And what we are trying to do is essentially minimize this potential energy functional, as I'm showing over here. So it has these two contributions, this quadratic form and this linear form, which comes from this the right-hand side. So the idea is now to minimize this integral. And in order to do this, what we do is we divide this domain into smaller triangles. And then we integrate each of these contributions over the small triangle using numerical integration, and then sum it up to obtain the loss for the domain. And that's what we are going to try to minimize. So here I'm showing you the decomposition of the domain. Here in all, we use about 1300 triangle, and we use quadrature order from second all the way up to seventh order quadrature rules to compute the integral over the...
Ritwick, why'd you do that, just to compute the integrals? So
yes.
The triangles are basically Gauss quadrature.
The triangles are essentially decomposition. The Gauss quadrature points are inside each of these triangles.
Yeah. That's what I mean.
Yeah. And then exactly, George. That's what, to integrate these two terms, to obtain these two integrals, essentially, as shown over here on the top. That's what we decompose this for. Yeah, and so over here on the top middle part, I'm showing you the training loss for these different quadrature rules, and you can see, how quickly the loss flattens out, and almost about 200 epochs, the loss just flattens out. It didn't matter how many more epochs we trained it for. And actually, the switchover from Adam to LBFGS happens at 500 epoch, and you can see it didn't matter over here. It just flattens out. And on the left side, middle, I'm showing you the TFI solution, and below that, I'm showing you the absolute error of the TFI solution. It is the deep roots. Ritz also gives a good solution. As you can see, point-wise, we are getting a pretty accurate solution. And in the middle, I'm showing you the norm of the gradient of the solution, and below that, the norm of the gradient of the error, which is also pretty good. But I want to remind you one thing. For the collocation approach, if you go back a couple of slides, for the same problem, we achieved a much higher accuracy of, as you can see, e to the power minus 9 in absolute error for the solution. So the Dirichlet is not as accurate as the collocation approach. So then we looked also at the potential energy, because in the Dirichlet, that's what we are trying to minimize. So for this, at the bottom right table, I've noted the exact potential energy, and below that, the potential energy computed for the collocation method. And note that the exact potential energy is kind of the lower bound. We couldn't go below that. And you can see the collocation approach gives us very close to the exact value. And the top table, I have the potential energy for the different quadrature rules. And you can see in all cases, it is higher than the collocation and also for the from the exact value. And so, again, to conclude here, the deep Ritz is not really, it's not, I'm not trying to say the deep Ritz is not an attractive method. It is quite an attractive method. It is a good balance between performance and accuracy, because for the deep Ritz, we are only computing the first order derivatives, as you can see over here. So it is a nice method, but it's not as accurate as the collocation approach. So this problem, the nonlinear Poisson problem that I'm going to show you next, this we obtained from the work of Urban, and it's again the unit square, and on a unit square I'm showing you the boundary conditions, and this function f is shown over here to match this exact solution, the form of the exact solution. And for the purpose of training, we took exactly the same setup that was used by Urban et al. We have two hidden layers of 30 neurons each, and the training with 10,000 epochs of Adam followed by 20,000 epochs of LBFGS. And I'm showing the training and the testing points on the top row, and the loss is also presented over here. The switching happens from Adam to LBFGS is at 10,000 epochs. And in the middle row, I'm showing you the solution, and notice the highly oscillatory nature of the solution over here. And TFI is able to capture the solution quite well. The right plot in the middle row is the absolute error that we achieve. And in the bottom, I'm also showing you the gradient of the solution, norm of the gradient of the solution. And this is also, you can see, very highly oscillatory nature of the solution in the domain. And TFI does a pretty good job of capturing this as well with a pretty good accuracy, as you can see at the bottom right plot. So once again, this kind of a problem also is going to be hard with a soft imposition of the boundary condition. So this is another advantage that we obtain for exactly imposing the boundary conditions. So far, the problems that I've shown you, the geometry of the domain is fixed, and we have solved these different problems on a fixed geometry problem. So the question is now, can we train a model which can predict the solution for a family of geometries? So here, the solution that we are going to predict is for this, again, Poisson problem, and we have a zero boundary condition, and the geometry is as shown over here on this right figure. So the top edge over here, we parameterize with this parameter p going from 0 to 1 as shown over here. So for example, if you set p equal to 1, then y becomes 1, which means it becomes a unit square. And if we set p equal to 0, then y goes from 1 on the left to 0.5 on the right. So we get this quadrilateral. So we want to be able to predict for values of p going from 0 to 1 for this entire family of quadrilaterals. And the exact solution in the xy coordinate plane is shown over here. And to solve this problem, what we do is we transform from the xyp space to psi eta p space. And in the next slide, the motivation will become clear using these transformations as I'm showing over here. And the loss function, again, is shown at the bottom, where the UTFI now is in terms of psi, eta, and p, and so is this function f. The forcing function is also in terms of psi, eta, p. J, the Jacobian, is as shown over here. So the idea over here is, if you consider this XY space, this is the quadrilateral parametrized in terms of this parameter P. With the transformation, when you go map this to this xi eta space, it becomes a unit square. So once you have the unit square and now you think about the P direction, the other direction, the problem domain becomes a unit cube. So that's the advantage. And so now what we do is we take any xi eta plane and we lay out this grid of points as shown over here. This is the training grid. And then we repeat this plane for different values of P going from 0 to 1, in this case in increments of 0.1. So that was the reason why we thought this transformation helps us basically discretize this domain. And once we have trained the model, then we are going to come back to the XY space and predict the solution on these testing points as I'm showing you over here. So again, here I'm showing you the training loss. So once now we have the model trained and we want to predict the solution. So I've selected these 3 different values of P, which is different from what we had in the training data set. And for each of these values, in the top row, I'm showing you the exact solution. You see the 3 different geometries. And the middle row, I'm showing you the solution obtained from the TFI. And the bottom row shows the absolute error. And you can see for all the geometries, TFI gives an accurate solution to this problem. So now let me shift on to a different type problem. Here we try to solve an inverse heat conduction problem, but on a pentagonal domain. So the problem is again.
Wait, how many more slides you have?
I have just three or four more slides.
Okay, because way past the time now. It's
time now.
Minutes.
Okay.
Yeah,
okay. So I'll go over a little more rapidly for this problem. So here in this pentagonal domain, what we have is essentially 0 boundary conditions on all the faces, gamma 1, gamma 2, and gamma 5. And on gamma 4, we apply sine pi s, where s is a non-dimensionalized distance going from 0 to 1 on this edge. And for this problem, the function f, which is this forcing term, we take as this simple linear form, 60x plus y, and then we solve this forward problem using the finite element method, using abacus with a very dense mesh of quadratic heat transfer elements. Now, once we have solved this problem, now we pose the inverse problem. Suppose we sample the exact solutions at a few points in the domain. Can we discover this forcing function or heat source function that was applied in the forward problem? So that's the inverse problem. And note that now we'll have 2 different contributions to the loss, one coming from the PDE and one coming from the data loss. And what we do is we in the past we only had PDE loss. So now we have this additional data loss, and we weight the data loss a little more heavily because those are the ground truth. So here now I'm showing you the on the left side the randomly sampled location where we sample the solution. The middle is the training, and the test for testing, what we do is this is a dense finite element mesh, and we'll predict at the nodal points and compare it with the finite element solution. So we did 2 sets of experiment. In the first one, we assumed the simple linear form for the assumed heat source function, and then you can see the training loss at the bottom left plot. And in the middle, I'm showing you how this A0, A1, and A2, 3 parameters evolve over the training. And you can see pretty much at 40,000 epoch, we are capturing the solution. And here on the top row, I'm showing you the FE solution, TFI solution, and the error. We are able to solve this problem quite accurately. The bottom row, I'm showing you the heat source term that we discovered and the error in this. And here now I'm actually also showing you the second experiment we did with a quadratic form of this. So we discovered the 6 parameters, and I'll quickly show you the solution again. At the bottom, you can see over here, we have discovered the 6 parameters quite accurately by around 65,000 epochs. A1 and A2 are very close to 60, and the other values are pretty much 0. Again, here the solution and the discovered heat function at the bottom. So the TFI does a pretty good job over here. I'll finally end with this last problem, which is the econol problem on this pentagonal domain. We have 0 boundary conditions everywhere. So the exact solution to this problem is actually the sign distance function. And this is the training and the testing points. And now I'm showing you in the middle, the numerically generated solution. The sign distance function on the left is what TFI predicts, and on the right we have the absolute error. So this again is a fairly complex. You have the sharp corners that the solution has to capture. So I'll end over here in the interest of time. So just to summarize, we followed a very simple training procedure, but with the TFI we are seeing we are able to capture the solution accurately for different types of problem, forward, inverse, and parameterized problems. And that is all I have. If you have any questions, I'll be happy to answer them.
Thank you very much, Dr. Roy, for presenting the work, and Professor Sugu. But it was very interesting work. But I think in interest of time, maybe if anyone has any questions, they could reach out directly to Professor Sugu or Dr. Roy. And I would like to thank the speakers once again. And thank you very much. So if
Thanks.
Eduardo is here, Eduardo Monri.
Yeah, here I am. Can you hear me?
Hey, yes, I can hear you.